so, I'm going to be explaining in depth via code how this algorithm works and really give us a first introduction to scikit-learn. Then in the second half, maybe just the last hour, we're going to have another free-form exercise. I got a lot of good feedback about that last time, so I am going to try to give you some opportunities to practice the skill set. So you're doing a git clone, you're getting the content for today, you're going to open up git bash, cd to wherever you've downloaded that content to, cd change directory, and then type Jupyter Notebook or open up Jupyter Notebook however you have been doing it so far in class to get to today's lesson. In today's lesson, we have the code file, that's where you're starting off, and the code directory, that is. We're going to go inside of code to starter code. In starter code, we have two files. KNN sklearn is what we're starting off with. The MBA exercise is what we'll get to at the end of class. So this is the KNN sklearn IPython notebook that I'm starting off with. We're going to get to a bunch of exercises throughout this as well. So at least follow along if you weren't able to get this up and running. Yeah, so we're going to go through the model, scikit-learn, and talk about the supervised process as well. Now I start off with this lesson just as a continuation with that iris data set because the focus today is not on the data set, it's just understand how scikit-learn works. Don't really want to have to make any modifications to the data at all. Now in this case, what am I doing? I'm importing pandas. I'm looking at a URL because we can read data directly from a URL to pandas. I'm providing my own column names for the data set, and I'm saying pandas, read the CSV file. Read it from this URL. There is no header in the file. There's no column names in the existing file, so header equals none. But I do want to provide my own header names, so the names of the columns is the names that I provided in this list in this exact order. So we go ahead and read in this data set. After we've read it in, we take a quick look, remind ourselves about this data set, 150 observations, 50 of each of the classes, Setosa, Virginica, and Setosa. For the actual species, if I'm doing this as a classification problem, no missing data, all the values are using the same scale, and the, so that's the data set. I don't need to spend too much time there because we've seen it before, and this is just stuff to make it look nice on the projector. When we build models in scikit-learn, this is where we're going to have that first realization of why we learned all this stuff in pandas. We're going to use a lot of pandas today to get data in the right format. And one of the things when we're converting data to the right format for any machine learning model and any machine learning package. Now we use scikit-learn in class, this class, but there's a bunch of other ones that do generally the same type of thing. Scikit-learn, Keras, TensorFlow, PyTorch, GenSim, like a whole bunch of different libraries out there that can be used for building models. They all have a similar requirement of data needs to be numeric. So in this case, where I start off with species, so iris the data frame, species is a column, that are categorical or text values, the actual names of the flowers, Setosa or versicolor and so on. Scikit-learn can't deal with that type of data. It's letting us know, it will let us know if we don't do this with an error message saying, you've passed me text data, I need numeric data. We're going to do different types of transformations for the features, what I'm using to make a prediction, versus the response, the thing I'm predicting. Right now I'm predicting the flower name. That's the way we're going to set up the prediction itself. So I'm using the map functionality, which is one of many ways we could do this, to convert text values to numeric values. And this is creating a new column called species num in the data frame. And let's really look at this. So if I say iris.head, you don't need to type that one along. But if I look at it, I see there's 5 columns right now, 4 features, 1 response. After I run this code and run iris.head again, I now have a new column. So this is added a column called species num, which is purely a mapping from name to number. Setosa, I say replace that or map it to the value 0. Setosa always gets mapped to 0. If I look at the tail of this data set for the last 50 rows, where I have something different than Setosa, now we have Virginica, which is mapped to 2. So That's a simple exercise of we've converted our response to a numeric representation. Do the numbers matter? No. It's just I'm going to be predicting 2s instead of 1s. Now, one thing we might want to do in a case like this is actually take this dictionary and pull it out. So I'll say this is my labels, I'll call it. And then instead of doing mapping to the dictionary itself, I'll say map to the labels. Does the code do the same thing? Yes. Right? There's no difference in terms of the actual functionality here. But what's nice is that now I have access to the labels later on as a variable I can type quickly, as opposed to scrolling all the way to the top. Important, because we're going to build a model. And the model is not going to say, my prediction for a flower is that it is virginica, because the model is never going to see that data. The model is going to say, I predict that it's flower type 2. And unless we have access to this or scroll back up to the top, it's pretty likely we're going to forget, well, is 2 Setosa or virginica, or what flower does that actually map to? So I like to do this with all my labels, just have nice access to it later on, and I can always just type labels and see that data. But that's the first process that we'll go through in every single further class after today when we're building a model. We will map any categorical data or text data to a numeric representation. Any questions about that? Okay, so we've looked at a couple visualizations in the past, and we saw that generally speaking there's a couple rules that we could have built ourselves to separate out these flower types. If I'm looking at this one right here, which is saying iris, drop the species none, the column we just created. Don't visualize that, but visualize all the other columns, the 4 features, sepal length, sepal width, and so on. And we're creating box plots by the species column. That's how I have, 3 different values for each one of these box plots, one for each of the flower types. The ROT 45 means rotate the labels 45 degrees so that they're not on top of each other. I can actually read these. And we saw that if I'm looking at, I don't know, have like sepal length, right, or sorry, this is petal length for this box right here, for this flower, which is Setosa, I can pretty much build a rule pretty simply that just says if it's below a certain value, it's definitely Setosa. If it's above a value, it's definitely not Setosa. So we went through that exercise of creating the rules ourselves. The reality of the whole rest of today's lesson, and actually many of the future lessons, is just automating that process so that we don't have to create the rules ourselves. That's all the model's doing. It's just we pass in data, and the model is going to look at the data to ascertain which rules are most likely to work to separate out these different classes. We do that because we only have 4 features here, and with 4 features, it's actually reasonable that I could spend enough time to create the rules ourselves. But if I had 4,000 features or 4 million features, you're never going to have enough time or enough creativity to really determine what are the best possible rules to separate out the data. So again, that's what the model is going to handle for us. We still want to do this exploration process of visualization to determine, does it seem like there could be rules? Right, like when I look at this feature right here, out of the sepal width, it actually seems like sepal width doesn't do the best job of separating the classes. It seems like maybe there's some sort of rule there I can use, but it's not something that's going to be really easy for the model. So the visualization process helps it with that step of saying, do I need to transform this data itself, or should I be collecting more data that's potentially more useful? How many plots do they have? Okay, so I'll look at this plot too. And a reminder, if we want to build something like a scatter plot, I could say, iris, plot, build a scatter plot, X and Y, so I'm picking 2 features. We can color the features with the C for color and give it a color scheme. And there's lots of different ones there. For these color schemes, we have things like red, green, blue, and that's the actual species that we're visualizing. You may have tried to do this last class, or 2 classes ago when I taught, and tried to actually color things, but found that you had a difficult time. And that's because when I'm applying color to a visual, it can work off of numbers, but it can't work off of the actual character names. So if you try to say C is equal to species instead of species num, so virginica, setosa, and so on, the full words, I'm going to run this, and eventually it gives me an error, and it says, and that is the column name, right? Yeah, species. So just saying that we don't know how to plot this data. Species num is numeric, though, and it's able to say that, well, 0 is less than 1 is less than, or 0, 1, 2. So these values are different, and it's basically just saying color everything the same for each one of the different values I have. And worse visualizations as well. Okay, so that takes us through just a quick reminder of the data set, and we can finally jump into the visualization or the algorithm itself. What I'm plotting right now is a way to think about the k-nearest neighbors algorithm. What's actually created internally instead of just these lines that I was drawing on the board. Now, the reality is that the model, scikit-learn doesn't exactly create this, but I find this to be a very good visual for actually interpreting the model. And I might show you later that this diagram itself comes from scikit-learn's documentation. So it's the way they think about it as well. What we have here is the data set, it's the iris data set. And we have 150 dots because there's 150 different training observations. We have the red, green, and blue. So instead of saying Virginica setosa, I'm just going to refer to this as red, green, blue. I think it's a little bit easier that way. So this dot right here is red, which means it is a red flower. This dot's green, which means it is a green flower. So the dots themselves is my training data. Data I've collected for which I do have labels, for which I pass into the model and I say learn rules from the actual data. The color scheme in the back, that's the model itself. That's what's created by the model. And the way of thinking about this one, what is this k value? This is k equals 1. So when I say k equals 1, that means I'm looking for the one closest point, and that's what I use for my prediction. So let's pretend I go on the ground, I pick up a new flower. I'm measuring its sepal length and sepal width, which are the features I have right here. And I have those data points. And I say that the sepal length and sepal width takes me right there. It's 2 and 4. So I know the observations, but what I don't know is the label. This is a new flower. I have no idea what the actual label is. Is it red, green, or blue? I can plot it right here, and the model, which is k equals 1, means I'm going to look for the single closest point. And right here, the single closest point is this red one. So when I say k equals 1, that means look for the closest point. The closest point is red. Therefore, this flower is red as well, and that's my prediction. Am I correct? Am I incorrect? I don't necessarily know right now. I just know that I have a prediction, and my guess is that it is red. Now, if I had picked up that flower and the observations were a little bit different, and it took me just past this line right here, well, at this point, the single closest point is not the red one anymore. It's this green one. So you can see this boundary right here just means, if I cross this boundary, now the single closest point is green instead of it being red. And that's what we have in terms of the boundary line here. I'm red, I'm red, I'm red, but the second I go here, now the closest point is that blue one, or maybe that blue one. Therefore, it's a blue prediction. So the color in the background is my model. The actual points themselves are the data that I use to build that model. Is this a good model? What are your thoughts? Does this look like a good model? Yes or no, and why? Yeah.
I'm kind of confused why there's blue dots within the green region.
So this one has an example?
Well, if you go down...
Oh,
So like right at the 6.
yes, that's a good point. Let me remind myself. The most likely reason for that is that there's actually like 3 data points on top of each other that have the same observation. Right, because there's 150 dots, but you can't actually see 150 dots here. So I bet if we look in the data set, there's 3 points that are green, green, blue, and they're all on top of each other. So that's my guess for why you see that.
Okay. Yeah.
Or someone did a bad job creating the visual, but it probably is the former.
Okay, because you can't usually classify it with thin lines. You can't generalize from.
Okay, so it might be a little difficult to generalize.
It looks decent if a little overfit. I mean, if you blur your vision, it's probably going to use an accurate.
Well, I mean, you used actually the perfect word there, which this looks overfit to me. Right, like if I'm looking at this one right here, Tyler is in like this whole region of green, and it seems a little strange that I make this one prediction for blue. Now the model is correct when I say k equals 1, that if I'm right here, the single closest point is blue, but is that really something that's going to generalize to the future, as you were saying? Maybe, but probably not. And if we blur our vision, you would almost say like, yeah, this whole region seems to be green, and this whole region seems to be red, and that whole region seems to be blue. So we would call this to be overfit. I'm giving too much importance to single data points. I probably want to generalize a little bit more broadly. So what do? We change one of our hyperparameters. I change the value of k. And instead of saying k equals 1, I now say k equals 5. And we get back this new map. And in this map, if we have some of these dots, like the one from before that was classified as blue, it's no longer going to get that prediction. Because if I say a point is right here, where before it would have been classified as blue, now we say, yeah, the one closest point is blue, but then 1, 2, 3, 4 other points are green. So I'm looking at 5 data points. 4 out of 5 are green, thus everything in this region is green itself. If I look over here, yeah, that point is green, and the single closest point is green, but it's surrounded by a bunch of blue ones, so we make a prediction for it being blue. And this model itself seems to be much broader, more likely to generalize into the future, less overfit than what we had before. Can we continue? Yeah, I can make the k value equals 15. And you can sort of see how the visualization is going to change itself. And the last one they have is where it's k equals 50. Now, by the time we get to k equals 50, I'm actually probably underfitting a little bit. That's saying I look for the 50 closest data points. And I don't know, there's a lot of green over here. I might say that it actually does seem like there's a chunk of green values, that there is a trend that we should be picking up here. But when we just look at 50 values, we sort of lose out on that. I certainly would say that only looking at one value is too overfit. So a lot of data science is looking at different hyperparameters and figuring out, where do we want to be in the realm, in the middle of really extremes of too small of a value or really extremes of too large of a value. We are going to figure that out, not actually today, but over the next 2 lessons where we start looking at evaluation metrics, a way of approximating, is this a good model or is it a bad model? Yep.
Should the k value follow like the size of the data set, or that's separate?
The k value is something you test separately, and it could be really like the best k value is not determined necessarily because I have 1 million data points or 10 data points, but it certainly does follow the size of the data set. And that if I have 10 data points, I'm going to need a much smaller value of k. If I have 10 billion data points, 50 might be overfitting still. I might want to expand that a little bit. So if it's the model predicting Netflix, which movie should I show where I have, let's pretend Netflix has like 10,000 or 20,000 different movies. Probably a different value of k than if I'm looking at human genomic sequences of which I have billions or trillions of potential values. Any other questions for just understanding how this works conceptually?
Do you ever use this KNN and sort of retain data on like areas of intermediate probability, like the breakdown is between like point by point say, all right, this is probably 60% blue and 25% green and 5% red.
So getting a little bit ahead, but it's a great question. Let's pretend I have 2 x's and 1 circle. And I'm using k equals 3. So this question mark is closest to 2 x's and 1 circle, and I tried to make them all equal distance away. What's our prediction? Is it an x or is it a circle? It's an x. There's 2 x's, there's 1 circle. I predict it's an x. If you had to take a guess, you want to give a probability around this, what would the probability be that it's an x? 63, 2/3. So can we have probabilistic predictions? Certainly. We can say 2 out of the 3 are x's, therefore it's 2 out of 3 probability, 66.66 repeated probability. Now that's going to change if I have 50 values, then I'm going by increments of 2% at a time. But that is absolutely a way that we can get back predicted probabilities. You'll see later on in the lesson, once I start actually coding this in scikit-learn, that we have 2 methods available to us making predictions, and most models have both of these. One is predict, is it an x or is it a circle? Another is predict proba, for give me back the probability of it being class A or B or C or whatever class.
Back to your example about like genomics data where you have like billions of data points,
Mhm.
wouldn't the overfitting almost make sense a little bit? Because like there's so many data points around what you're looking at to kind of, like is there a tipping point at which you actually don't have to generalize anymore and there is a really high level of assurance that this little pocket somewhere actually is sort of what it's being classified as?
That leads to a broader question of why we build models in the first place. We build models because I do not have all data and also because I can't see into the future. If I had a population of data where I had, let's pretend I'm looking for something right now where I can collect data on it and I could have access to every single possible data point. So that would be, I'm General Assembly's marketing staff and I'm determining who to market to predict that they're going to actually come to the class. If I had data on every single person and their likes and their interests and their aptitude of technology, I don't need to make a prediction. I build a rule or I just make a decision off of the data itself. We make predictions because normally you don't have all of the data available. The more data you have, the more you get into that realm where sometimes you just build a rule. And is a rule simpler than a model? Yeah. Like if you can build a rule, you should just build a rule. You're gonna, it's gonna be much simpler for you in many ways in terms of building the model, time spent on that, getting in production. But we build models when we don't have rules. You always want to have more data if you can, assuming it's high quality data. But more data makes our models more stable, gives us better predictions, but we don't always have access to more data. Yep, and then you're next.
Just a general question about like how far you go with the data before you determine it's viable or not viable, and like I just keep coming back to that as I've been like thinking about the project. Is like, do I have the right data? How much time should I spend manipulating the data before I say, okay, this isn't going to work, or I don't have the
As little time as possible. The approach that I highly suggest for all of you to do is you start off with the data set, and I don't care if you have 4 features or 4 million features, you pick 2 or 3 of them. 2 or 3 that, based off your business knowledge, that you say, these are probably pretty likely to be predictive. You go ahead, you spend a couple minutes exploring it, just a little bit, and you try to build out a model. The one we're going to show you later on today would work perfectly fine, as quick as possible. You pass the data, really messy data, uncleaned up, into the model, you get a baseline result. And that baseline can tell you a lot of, is there any value potentially of this data set? Then you iterate over and over and over again, cleaning up only the data points that gave you that spark of insight that actually seems like there's some value of. The wrong approach to do, which I've done many times myself, and sometimes you just fall into this trap, is I have 10 features. I clean up the features as much as I can. I spend all this time cleaning them up. And then, days or weeks later, I finally get to the model and realize that actually none of those features were useful whatsoever and I wasted my time. So the only way you can determine if a feature is useful or not is you put it into a model, you have an evaluation metric, as we'll determine over the next 2 classes, and you say, did this data improve or not improve my evaluation metric? If it does, even just a little bit, that tells you that I might want to spend more time with this feature. And there's another question?
Yeah, I think it has to do with what you said about models are used for creating rules to separate out data.
Mm-hmm.
So I'm trying to think of my own data that I'm working with, like compliance and enforcement data. So this is like number of inspections that EPA does, universe size, meaning how many facilities, violation counts, enforcement. And I don't know the relationship between, these would be features.
Yes.
I don't know the relationship between these things, so I can't create the rule, right? So a model would be built to create these rules. Is that the idea, more or less?
Essentially, yeah, right? Like the model is determining, is a site in compliance or not? You're passing in data, number of checks they've had, type of employees, last time that it was or wasn't in compliance. You pass in all these features, and the model is going to determine or create the rules itself. Now I really shouldn't be using the word rules. I'm gonna keep using that for today because I think it's an easy way to think about it. Sometimes it's rules, sometimes it's probabilistic predictions, sometimes it's actually instance-based counts or observations as we have right here. So we're not actually creating rules per se right now. But the model creates some sort of statistical formulation from which it can make predictions in the future. And it does that because we can't build perfect rules or statistical equations ourselves always. You certainly can guide it. You probably have some pretty good hypotheses of what's useful and what's not useful. Use the model to validate or invalidate those hypotheses.
And that would be a classification scheme, like if it's in compliance or not, but can you think of how that would be like you can use in terms of regression, you said?
Yeah. When do I think it's going to be out of compliance? How many days until it's going to be out of compliance?
Oh.
Right, that's a continuous range. And if that's the problem you have, which is not, are you going to be compliant or not, but when do I need to do enforcement action to stop you getting out of compliance? Well, if you're a year away from getting out of compliance, maybe I don't need to do that. But if you're a week away, then I definitely need to prioritize, giving you some sort of enforcement action or something like that. So that, I'm not saying that's the best problem, but that is a way that you could formulate it as a regression. Okay, so let's keep moving on a little bit here. We have our machine learning process here. What are we talking about right now? Just the top. I have training observations. In this case, it's the actual flower observations. I have labels for those flowers. Flower red, green, blue. I pass those into k-nearest neighbors. That's our algorithm. And I'm going to do this process over here of tuning it. I tune the value of k. I tune the weighting scheme. I tune all those 4 things plus others that I was talking about. And that's going to give me eventually a predictive model. We take the predictive model, and now I pick up a new flower, pass the flower through the predictive model. Model gives me back prediction, the expectation that the model has of a given label. This leads us to the model itself. Let's actually write some code now. So we're going to use scikit-learn, and first and foremost, why do we use scikit-learn? Because it's not the only library that's out there. The reasons, and actually there's this article here I would suggest after class, or maybe during the break, take a look at that because it's pretty good. Is that scikit-learn is really powerful, and you will see that going from model A to model B, logistic regression to random forest, completely different models, one a parametric model, one a rules-based model, is the difference of 2 lines of code, and only 2 lines of code. So very, very minor differences going from one model to another. This class is meant for shallow, not deep learning. I'm going to show you lots of different models as opposed to just going really deep into the linear model. Right? Like you can take econ classes that are just only about the linear model. You spend entire semesters on that. We're going to see lots of different models. So shallow learning of each one. And when I want you to be able to really quickly switch between the models, scikit-learn is perfect for that. Also, the documentation is absolutely excellent. Like they have code examples and long descriptions of the concepts and how the code works, and I'll get into that later on, but it really is adopted widely in the machine learning practice, not just because it's so versatile, but because it's so well documented. The code base itself, not something we get too deep into. You have to get next level of data scientists before you get there, or at least those of you that know object-oriented programming. It really just has like beautiful structure as well, and I frequently will actually read through the scikit-learn code base just to get ideas myself. Some of the drawbacks though, the initial process, it takes a little bit to get used to, but that's the nice thing about this 10-week class, right? We have a couple of weeks to really get used to this process, and then once you're used to it, it's just the same exact thing for everything. And what you'll notice is that scikit-learn is not just for the model itself, it's for the whole pipeline. So we're going to build models. All the transformations and modifications and evaluation of our model itself, that's all going to be self-contained within scikit-learn. And you'll see that the code of transforming a unit, so transforming miles to centimeters, is essentially the same process as building out a k-nearest neighbors model, same process as building out a logistic regression model. So you have this really clean API over every single possible operation you might want to do in scikit in the library itself. So once you learn the process, and it's just 4 steps, we're going to go through it today, you will really know how to use every single piece of functionality within the library. There's others, but let's actually get you into some code. Okay, so what do we need to do? We need to get data in the right format. We've done that for the labels already. We've changed text into numbers. Now we need to separate out the labels from the features. So this is a requirement. I have features as one object. I have labels as another object. I will always from now on call this X, capital X. Whenever I say capital X, that refers to all of my features. So in this case, sepal length, sepal width, petal length, petal width. 4 features. It's a capital, not a lowercase x, because in linear algebra, capital X refers to a matrix, and that's what we have, a matrix of data. When I say matrix, think data frame. We are also going to have lowercase y. Lowercase y refers to our label, our response, the dependent variable, so the thing that we are making a prediction for. So we just need to separate out these two, and you've seen a bunch of ways that we could do this in pandas. One way is I could list out manually the feature columns, and I say, here's my 4 features, and I'm going to create x. X is going to be equal to iris, the full data frame, filter to just those 4 features. So if I run that code, and then I'll create a new cell just so I can look at it for a moment, x, and I'm just going to say x dot head. Okay, so what is x? X is the data I'm using to make a prediction. It's my observations, but not the labels of those observations. So that is x. By the way, there's a lot of other ways we can create this. So here's 3 other formulations that does the same thing. One that I like is this one, this first one. When you have 4 features, it's not that big a deal of just writing out the features yourself. But when you have 400 features, it'd be really annoying to type them out one at a time. So it's actually easier in that case to say everything except for the labels. So these are 2 different ways that we formulated the labels. So just keep everything except for those. Drop those 2 columns. This also is a good example of the in place equals true. We are purposefully not doing in place equals true. When I say drop column species and species num, I don't mean delete these columns. I still want that data. It just means temporarily ignore them from the view of my data frame so that I can only retain the features that I care about. So there's other ways. I don't really ever write it these other ways, but yeah, it's there. Yeah, what is y? Y is our response. Normally, in this class, we are just going to use one response, meaning species num. I'm making a prediction for the numeric representation of the species value, 0, 1, or 2. So we have our x, we have our y. The most common problem that people run into when you're using scikit-learn is that you have the wrong shape. So the shape of x must be, not even the shape, the type of x must be a data frame, right? So many columns of data. So if we look at x, and I say, what's the type of x? It's a data frame. What's the type of y? The type of y is a series. Single column of data, series. Many columns of data, data frame. Needs to be set up this way. Another thing that's important is that the shape or size of x and y must be the same. If I have 150 rows of data, I need 150 labels as well. I can't say here's 150 rows of data and here's 20 labels, because the model's just building rules. It's saying, when we look at our original data frame again, so let me do that down here. The model is very specifically saying, okay, we look at the first flower. The flower has 5.1, 3.5, these observations, and when I see observations like this, I have a little bit more evidence that it's going to be a setosa, value 0. We then do the same thing for the next row, the next row. Thus, we need the data, and we also need the label for that data. So if I pass in, this row of data, but I didn't provide a label for it, then the model doesn't have anything to learn from. I mean, there's other types of models that do that. The unsupervised models don't have labels, but that's not the space we're working in today. We are working in supervised, so I need data and the labels for those data points as well. Okay, so what I want everyone to do is type along. And the first couple of times we write this code, I am going to enforce, not just show it on the screen, but have you type it. This is a process that really should be memorized 4 or 5 classes from now. So step 1 of every single thing in scikit-learn is we're going to import a model. So we're going to say from scikit-learn, and in this case we're in the neighbors package, so scikit-learn.neighbors. I'm going to import, and I'm importing a model called k-nearest-neighbors classifier. K-neighbors classifier. So let me leave that on the screen. I'll come back and explain a little bit more of how would I know to type that offhand. It's actually pretty quick for you to look at the documentation to figure that out. But this one, I'm just giving to you. We're importing something from scikit-learn, which allows us to build out a k-nearest neighbors model itself. I'm then going to copy that word k-neighbors classifier, and step 2 is we have to instantiate it. So we have the functionality in memory that we can build models. We haven't done that yet though. So the instantiation means, the simplest incantation is I just say k&n is equal to an instance of this k-neighbors classifier. All right, so to really understand what's happening here, you kind of need to know object-oriented programming. Aside from that, the technical lingo is for creating an instance of the class k-nearest neighbors classifier. This right here is coming from scikit-learn, and it has the functionality to build out all different types of k-nearest neighbors models. What are the different types? Why is it not just one type? Well, because we have some selections. I select the distance, the weight, the k-value, and other things like that. So this code right here is saying build out the generic k-nearest neighbors. And for that generic one, let's call this one instance, this one of potentially many k-nearest neighbors models, let's call it k&n. I can choose a name of whatever I want for this. This is just a variable. So I could have read out the whole word. I could have said model 1, anything you want's there. I normally write out k&n when I'm building k-nearest classifiers. The moment that I run Shift-Enter on the import statement, that means that I brought in two things. The actual code for k-nearest neighbors, but also the documentation. So note I had to do that for this next step to work. And that next step is I go inside of k-nearest neighbors inside of the parentheses and I press Shift, Tab, Tab, and as I said, I brought in the documentation. You're not going to see anything here until you do the import statement, but now I have the method signature. I have all the ways that I can modify this algorithm. And what do we have? N neighbors equals 5. N neighbors is the k value, which means by default, the value is 5. So they give you default values. And if I just say build the default algorithm and I don't pass in any hyperparameters, come back to that word in a moment, it's going to build out these hyperparameters here. So n neighbors equals 5. The number of, or the weights is uniform. Every single data point gets the same weighting scheme. You have uniform, you also have, what's the other word? Scale, or uniform, or distance. And distance just means the inverse of the distance. Further away, less weight, closer, more weight. What else do we have? We have a couple things I don't want to get into yet. Algorithms, leaf size. These two together, the metric equals Minkowski with a p-value of 2, that actually just means Euclidean distance, right? So that triangle distance. So we are using Euclidean distance, that's the default. This is the statistical name for it, but it's doing the same thing, and somewhere in the documentation actually tells you that. And those are the ones I want to talk about so far. So we have the same hyperparameters that I had already shown you. Those are available. I'm not going to get to those yet. I'm not tuning anything right now. I'm just building the default model. So at this point, we have the instance of the default model. Now I have the functionality to build a k-nearest neighbors model with these selected hyperparameters. Hyperparameters is the key word there. When you have a function, you have parameters of the function. So if I have the function sum and it takes in x1 and x2 or num1, num2, those are parameters of the function and then it returns the sum. When you are building a model, we use statistical lingo. And the lingo, when I have a parameter of a model, we actually call that a hyperparameter. So it means the same thing. It's a parameter of the model, but you'll hear people using that terminology, so I want to use it as well. We haven't built the model yet. We've just said, I have the functionality to build a k-nearest neighbors model that uses n neighbors equals 5, and it uses uniform weighting, and it uses Euclidean distance. If I had gone ahead and I'd changed this, don't do this yourself, but I made it n equals 6, and I run the code again, well now I have a new model. I have a model that can build neighbors equals 6, so it's going to look at the 6 closest data points instead of the 5 closest data points. So we haven't trained the model, we just set it up so that it can learn in different ways. One model counts 5 things, another model counts 6 things. if we want to actually build the model, we need to fit the model. It's an aside here, and you don't even need the print statement actually, but if at any point we just print out this model, it's going to say, okay, for this KNN model, here's the hyperparameters that you use. Okay, so step 3, fit. When I fit the model, I say KNN, the model name, dot fit, and I'm fitting it with X and Y. Let me be extremely clear right now. I'm doing something tremendously wrong, and we're not going to correct it in today's class. We're not going to correct it until next class, because I can't teach you everything of the entire modeling pipeline. I'm doing something horribly wrong right now, and that this model I'm building absolutely will not generalize, and I'm breaking many rules. We need to learn this way, though, first, just to get an understanding of the process, and then we're going to look at evaluation metrics and figure out how to fix this. The problem I'm making is I'm not splitting my data into a training and a testing set. I'm just learning from all the data. If you're not familiar with that, don't worry about it. This is okay for right now, because we're just focusing on the scikit-learn process, not the data modifications I need to make before I pass it to scikit-learn. But I go ahead and what's my problem here? What's the mistake I made? Y is not defined, so I forgot to run the code that creates Y right here. So I build my model. And at this point, I essentially just created that color map that I showed you at the start of the screen, at the start of the presentation. So I actually have built a model. This model is ready to go. I can make predictions off of this right now. It's the entire process. All right, so scikit-learn is abstracting away all of the code of the actual formulation of the algorithm. Although I sort of explained it already. The algorithm for KNN is pretty simple. Measure nearby points. I'm going to talk a little bit more about it later in today's class, but you can see when you're using scikit-learn, the pro and the con, pro is that it's very simple. That's the whole model. The con is that sometimes it abstracts too much away for us. So we want to have somewhat of a better understanding of what the model is doing, at the very least at that conceptual level.
So hyperparameter leaf size?
Say again?
What is the leaf size?
The leaf size actually gets into the algorithm itself. So let me not explain that right now, but that's one that you almost never would actually tune yourself. It's more so in the speed of how quickly you get predictions as opposed to the predictions you get back. You're going to see some of the algorithms that we go through have like 50, 60 hyperparameters, just like Pandas Read CSV had a lot of options. We're not always going to touch everything. I'm going to get to some, we're going to cover more of the ones that I have here, but not all of them. But let's right now just focus on the process itself. So I import the model, I instantiate the model, I fit it, and at this point I'm ready to make predictions. So I can say knn.predict. And I'm predicting on X. I've trained it on features, sepal length, sepal width, 4 features. I'm going to make predictions off of those same features. And if I predict it off of X, well, X itself had 150 rows of data. I'm passing in all 150 rows of data, and I'm getting back 150 predictions. So we can do this in a couple ways. Let me come back to this one in a second, because, let me do it this way first. Show you X where I have only one row of data. So I pick up a flower, I say the sepal length is 3 and sepal width is 5. Right, so I have 4 observations, 4 features for one flower itself. I take X new, and I say for this one flower, give me a prediction. You can actually see we're going through the whole process here. Instantiate the model, fit the model, and then give me a prediction on X new. When I run that, I get back one prediction because I passed in one data point. So this is kind of crazy when you think about it, right? This is the entire code to build out a model. It's pretty simple. So X new is what I passed in. I said, maybe give me a prediction because I don't know the label for this. And the label it predicted is 1. Well, what does that mean? What is 1? Well, that's why I had that labels dictionary from before that I saved. And I can remind myself that 1 is, that's versicolor. So that's the prediction of the model. I don't know if it's correct or incorrect. That's stuff for next class, but I at least have built the model and gotten back a prediction from the model itself. If instead of saying X new there, like I had above, I had said predict on X, the entire data frame, all 150 rows, it gives me back 150 predictions. So you can see that way I can change the number of predictions that I pass in. And what's kind of cool here is we remember in the data set that there's 50 of the first flower, then 50 of the next flower, and 50 of the next one. So you can sort of see from here, it says, well, 0, 0, 0, looks like the first bunch of flowers get the same label, and then a bunch of the next flowers get the 1, and then the last flowers get a 2. It's not perfect, right? We have a 2 right there, we have a 2 right there, those are mistakes. But at the very least, it seems to be picking up on some trend of the data set itself, that even with this simple model, with no tuning whatsoever, it's learned something about the data set. Again, I validated a lot, or invalidated a lot of statistical rules building this first model, but just gives you this inclination of how it works itself. So let me pause here, let's look at the code, instantiate model, fit model, make a prediction. You will be typing this type of code hundreds of times in this class, so please, if you have any questions about what's going on there, ask now. Okay, so at this point, we've built our first model. We've built a k-nearest neighbors model. We built it so that it gave us back predictions. Let me just see what we, okay, cool. So other things we can do instead of just saying knn.predict is I could predict the probability. And let me run that one again. Can anyone take a guess? When I say knn, not predict, but predict proba, what do these 3 values represent? Why do I have 3 values for my prediction instead of just 1?
It's the likelihood that they actually fit into what predicts they're going to be. Something like our x and zeros over here, where it was like 0.6, because 2/3 of the points were.
Okay, so the 3 values represent the 3 flower types. Yeah. All right, so flower type 0, flower type 1, flower type 2. So Toaster, Virginica, and so on. So it says that, okay, it's definitely not flower type 1, 0% probability. We're pretty sure it's flower type 1, 80% probability, 20% likelihood of the other. And if you think about this, we had k value of 5, which means that 4 of them were type 1, 4 of the closest values, and 1 of the values was type 2. So that's how we get back the probabilities. You will find that some models are explicitly tuned to give you back great probabilistic interpretations. Logistic regression is one model we'll look at, that in the equation itself of logistic regression, it uses something called a logit, which has a direct transformation to probability. In this case, we don't have probability in the equation, right? We have distance metrics, that's what we're focusing on, and we have a way of approximately using distance metrics to equate that to probability, but we're not tuning the probabilities. So that means that these are okay. I put some trust in them, but it's not, if I really care about the probabilities, it's not my first model to select. So just an aside there that I'll come back to throughout this class. Okay, we've built a model, we predicted, we also got back predicted probabilities. Let me use this as a moment to go to some documentation. So if we want to look at documentation for any model in scikit-learn, I'm going to say scikit-learn and then the name of the model. So in this case, we're using knn. I don't even need to write out the whole thing, just knn. Probably the first link that you're going to get back is kneighbors classifier. So I'm going to click on that. And let's look at a couple points here. I had mentioned that we do this import statement, and I said, I just pulled it out of thin air, but how would you remember how to actually do that import statement? The first line of the documentation, from scikit-learn.neighbors, the thing in blue, import the model kneighbors classifier. So eventually you might start to memorize this, but if not, you say, I want to build a decision tree or a random forest or a KNN. The first link is going to tell you right at the top, from this place, import this model. And the way it's set up is that there's a whole bunch of different models in scikit-learn. So if I go to the home page, we see that we have 6 main areas of scikit-learn, and we will touch each one of these in the class. We're in classification today. We're building a classification model. So let me focus there, but you see there's regression, unsupervised techniques, pre-processing, and model selection as well. Inside of classification, I then have all sorts of different types of models. So we have linear models, support vectors. We are in the neighbors models, so nearest neighbors models. And if I go to, well, let's go back where we were. Yeah, so easier way of clicking to this is I just click on scikit-learn.neighbors itself. It is a link. And it's going to take me directly to all the different neighbor-based algorithms that I have. So in this case, we are using k-neighbors classifier. But you can see there's a whole bunch of other algorithms that are all start off with neighbors, that are counting distance metrics and so on. Very different from our decision trees or our linear models or other things like that, right? So if I scroll down, we have neural network models, and we have, that's later on in class. Naive Bayes models, we'll look at those. We have, anyhow, lots of different sections. Just to show you that it's set up this way, unlike pandas where I say import pandas, import the entire thing. It's because you're probably going to use a lot of the functionality of pandas. When you are in scikit-learn, you're kind of focusing on just one thing at a time, right? Focus on the k-nearest neighbors model. Scikit-learn is this huge package, and if I imported everything into memory, it's going to be annoying. Like I'm going to really clutter my memory space with a lot of code that I'm not using. So when we use these types of packages, we're specific, and we say, from this place in scikit-learn code base, import that model. I can actually show you, I'll do this at the end. I'll show you what it actually looks like in the code files themselves, so that makes a little bit more sense. But could we do import scikit-learn? Yeah, that's totally fine. That would work. You just never are going to see anyone do that because there's too much of scikit-learn and it doesn't make sense to import everything. Okay, so inside scikit-learn's documentation, we next have the method signature. What can I do to tune this model? My hyperparameters, neighbors equals 5. Directly under that, I'm going to have the explanation of these. Neighbors, it's the number of neighbors that you would use. It's the value of k. Weights, we have uniform distance or a function we can create ourselves. So explanation of those hyperparameters. If it still doesn't make sense, most models have a user guide. So if I click on this for a second, it takes me to just explanation of what is k nearest neighbors. Like how does this algorithm work at a conceptual level? And there's a lot of details. You can see where some of the diagrams I used came from. Describing nearest neighbors classification and regression. And there is a lot of documentation. I actually have read through the entire code base, the entire documentation base, but it took me like a year of doing that on the side. So there's a lot there. And I would recommend, especially for the models that we use, read through the documentation outside of class because it's helpful to get a better understanding. But we have these hyperparameters, decent number of descriptions there. Then I have the methods. Well, actually, before that, I have a full example. Note these like 3 greater than symbols there. If you click on that, it's just the code, so I can copy and paste it. Click it again, it gives you the actual results of the code. But this is what I just went through, right? Import the model, instantiate it, fit it, and then make a prediction. So we went through the 101 example so far. Now where would I learn to use fit or predict proba? That's with the methods. And we've actually already used 3 of these. Fit, predict proba. There's other things we can do as well. Most models are going to have at least those 3, plus some other things that are model specific. We have explanations of each of those. What does fit mean? What does it take in? What's the hyperparameters? So lots of documentation for that. Another example. And then all the way at the bottom, they have Jupyter Notebook examples showing you how to use this on larger code. So this code right here is not the same, but pretty similar to what we're doing. So we see we have neighbors, we load in a data set, we have our X and our Y. Like it's the whole process of building a model, and they have this for every single one of their models. The only downside about this documentation is that it looks like a lot, but 90% of this code here is just code to actually create these visuals. So they always give you the code for the model and the visuals, which very rarely do you actually need to replicate this visual. You want to replicate the code, underline that visual, but at the very least, it's nice that they do this with many different notebooks. So lots of examples for K and M. That's the general documentation, so conceptual and also technical overview. For every single model, the last thing I said I was going to get to is the source code. And there's this source button, which takes us to GitHub, because scikit-learn is on GitHub. I actually have a student from a previous class who made a contribution because they found something they wanted in their project, and they added it to the code base. When we get there, I can point that out. This is code that we don't get into this class. You certainly can talk through any of it during office hours if you're interested. This is object-oriented programming, so it's more of the data engineering skill set as the pure data scientist. But I want you to see, first of all, just an example. Like when we have real code here, data engineering codes, code of the person who's creating the library, look at the ratio of documentation to actual code. So here's the name of the code. So that's code. The class is k-nearest neighbors classifier. We're looking at the actual implementation. Now we have documentation, documentation, documentation. And then for that amount of documentation, we have this set of code right there. So normally it's about a 3-to-1 or more ratio of code to documentation. And that's the reason why scikit-learn is so popular, more so than anything else. And then, this code here is using object-oriented, so it's very different from the Pandas stuff that we've created. But you can see we have the code to make a prediction, again, documentation for that, and then code itself. And it does look like a lot of code, but about 90% of the code base is not build the algorithm. It's just figure out everything that a user might make a mistake in. So they have the wrong, what do we have here? The shape of the data is wrong, so I pass in a series instead of a data frame for my x values. The number of classes that were provided is incorrect. I provided 2 classes when it's just 1 class that we could predict on. There's empty values in my data set. You can't have any empty values, so we must populate or impute everything. So you can see like 90% of the code base is just thinking, what can you do wrong, and then giving you an error message. Again, one of the reasons why it's such a popular library. Bigger point here, though, is let me go to the main page of scikit-learn, sort of like our main page of our class. There's a bunch of files here, but the one we care about is scikit-learn, the actual code base. Inside of scikit-learn, I have a bunch of subfolders. One of those subfolders is for the, neighbors. From scikit-learn.neighbors. And inside of neighbors, I have a model called classifiers. See classification somewhere? Yeah, classification. All right, so from scikit-learn.neighbors, import a file, or import the class k-neighbors classifier. All right, so it doesn't completely explain how all these files work together, but at least it gives you some sense that this import statement we're doing, we're just reading through the code base. Look at the whole code base, look at this subfolder, and then pick a model from a specific file. That's what we're doing. Okay, so that takes us through a high-level overview of the documentation. We will go, actually, we're close to the end of this notebook, so let me finish this one, and then we'll take a break and jump into an exercise after it. So here's what I want you to do as just mini exercise within this notebook. We've set up a default model. Let me go ahead and change the model itself in this code right here. Instead of neighbors equals 5, I want neighbors to be 10. So I'm going to change it to 10. I'm then going to fit that model with x and y and make a prediction. And I don't know if it's going to change, but let's look at the prediction that I get back from this one row right here. If I change that from 5, nearest data points to 10, does it change the prediction? Goes from 1 to 1, so it doesn't change. What if I make it 100? Right, so if I make it 100, if I look at the 100 closest points, all of a sudden it's giving us a different prediction. So we haven't decided yet if that's a better or worse prediction, but we do see that we can try out lots of different models, which may give different predictions. So as an exercise, what I want you to do is go through the entire process here. You're going to instantiate the model, you're going to fit the model, you're going to make predictions, and then I've actually given you a little bit of code for evaluating the accuracy. But what I'm asking you to do is not just build one model, but rather, here's a range of k values from 1 to 100. I want you to set up code that's going to test out 100 different models, 100 different values of k. So you need to change that hyperparameter. So, I'll give you 3 or 4 minutes to go ahead and try to type out this process. Anyone have difficulty opening up the file? Any questions like that? species number when we created that column. We forgot to hit the shift enter. And you'll see me do it 1,000 times in class. That's pretty common. It was seven. I don't know. Or you can just go to the top and click there. I hear the typing slowing down, so let me just go through this. We're going to go through a much longer exercise, so I have lots of time to practice. What are we doing? We're going to try out a lot of different models. So most of this could be copy and paste. I would ask for these exercises, try to type things out, and always try to do it from memory first. You're never going to be able to do the whole thing from memory, but start off that way so you can refresh yourself of like, what are the things you don't memorize, especially for this 4-step process, because we do it so frequently. So I could start off, I could say build out the k nearest neighbors classifier, but I need to modify something inside of the parentheses. What should I change? And neighbors. Note I have a documentation in memory, so I pressed the first letter, tab, and then for most of you, documentation should show up. So and neighbors is equal to 5, 6, what am I putting here? Okay, yeah, right, we're putting a variable as opposed to the number itself. K will take on 1, then 2, then 3. Every single time I'm going to build out a different model as part of a for loop. Note I'm not starting with 0, because I need to have at least one observation that I look at. And we can think about this as overfitting, giving too much weight to a single point, to the point where I'm overfitting. I'm just, separating out the importance across too many values themselves. So this is K and N, our model, and that's it. Everything else is exactly copy and paste. Fitted on X and Y, and we're going to make a prediction. K and N dot predict, and I'm predicting on all of X. This is important to remember the order here. Fit, learn the features and the association of the features to the label. You can't flip those two. It has to be that order. Features to label. Then make predictions just on features. I don't know the labels. That's why I'm making a prediction. So we're going to expand on that in next class. But for right now, features, labels, when I'm building the model, just the features when I'm making predictions, because I'm asking for the labels. And since I'm asking for the labels and then trying to do something with them later on, you have to actually store these. And I'm going to store them in the variable name pred, because it looks like that's what I'm using down here. Again, I do not trust these results. This is just for explanatory purposes. We'll fix it next class. But assuming this was correct, assuming I had passed in the right set of data here and I was evaluating against the right set of data there, all the rest of the code would be the same. What is this doing? It's saying we're going to get back some predictions, And these predictions, which are going to be 150 values, because I say K, build the model. So the first model is K and N trained on 1. Look at the 1 closest observation, question mark. Closest observation is an X, therefore my prediction is an X. Fit it on all 150 data points. Then make a prediction on all 150 data points. Thus my pred for the first model is going to give me back 150 predictions. Those 150 predictions of pred are just predictions. I don't know if they're correct or not. What's nice is that I do have the correct values. Y is the correct values, 150 correct values. Here's 150 predictions. They're in the same order, so I can compare the two. And here we're saying pred equal to Y. Now if I run this code and look at what was the last example of pred, just so you can actually see what this looks like. Pred, I had 150, 0, 1, or 2, the actual predictions. What is Y? Y is the correct labels, 0s or 1s or 2s. You know, it looks different, but it's the same type of data. So the real question is, how frequently is pred the same as Y? How often are they equivalent? They're equivalent quite frequently. Well, we should see some falses in here, because I know I made some mistakes. And this is just saying, how many times was I correct? How many times was I incorrect? So pred is equal to Y is the Boolean series. I can take the sum of that, which just means calculate 1 for all the true values. 150 rows in total. Of those, there was 132 truths. 132 times that I was correct. If I take 132 divided by length of Y, the length of Y is 150, because there's 150 observations. And by the way, when you do this, even though there's 2 lines of code here, the only thing that's printed to the screen is the last line of code that was run. So the last line of code is length Y. There's 150. I was correct in 132 of them. So if I say the 132 divided by 150, I get back 0.88. In the old version of Python, we had to use float here. We actually don't even need that anymore. So I can simplify the code there. No problem using it, just you don't need it. That's the score. So for the first model, where I looked at k nearest neighbors equals 1, I was correct 88% of the time. Thus, I'm going to append to my scores list. What is this list? It's a list all the way at the top, an empty list to start off with, but I built one model now, so I'm going to append to that list with k equals 1 and the score. 1, 88%. Now that's just the first model. We're doing this 100 times. So then I build model 2, get 150 predictions, look at the accuracy score, add it to the list. Model 3, model 4, and if you look at the 33 right there, it'll turn into an asterisk when it's building the model. So like anytime you're using a Jupyter Notebook, asterisk means code is still running. You're not going to be able to do anything else. So 3, 2, 1, look at the 33, and it's done. Right, so I build 100 models in essentially half a second there. So it's a small data set. It's obviously going to be very quick building that out. But at this point, I have 100 models, 100 predicted accuracies, and we can plot that. And while the results will change next class, the process will stay the same, where we are looking at a little bit smaller so we can get on the screen, not larger. Okay. We are building a data frame. So I'm saying this scores list, turn it into a data frame, give it columns of k value and score. So if I just looked at data right now, this is the data frame. K equals 1, the score. K equals 2, the score. K equals 3, and so on. So we have all these different scores. And then we plot it. And I'm building a line plot, looking at the x value k, the y value, the score. And we see this plot. What does this mean right here? So when I have the value of 1, like, what does this mean conceptually?
Well, basically mirroring like what the existing data set is.
Yeah, so it's mirroring the existing data set. If this was correct results, this would be 100% accuracy, so it would be a perfect prediction. And anytime you see a perfect prediction, that should scream out to you that you've made a mistake. You don't ever get perfect predictions. Inherently, if you've done that, you've messed up something earlier on. Things we will fix in next class. And otherwise, we would look at this chart and we would say, oh, it seems that as I increase the value of k, my predictions are getting worse. Now, what we're going to see starting next class in terms of these types of graphs for given hyperparameters is that they normally have a upside down U shape, at least when we're looking at accuracy as our evaluation metric, which means at some point we are overfitting. We're giving too much importance to individual data points. At some point we're underfitting. We're not giving enough. We're looking at too many data points that are irrelevant. But in the middle, we have this nice, not too hot, not too cold situation where we have the ideal hyperparameter. And I don't know what the correct one here is, but let's call this as an example like k equals 15, that's k equals 1, and that's k equals 150. So somewhere in the middle, not directly in the middle, right? Not necessarily 75, just somewhere in the middle. How do we determine what's the best? We create charts like this and look at other statistical measures we'll see in later classes and use this to guide our decisions of what are the optimal hyperparameters for a given business problem. So this is the general process of scikit-learn. Format our data for the model. Select a model that we want to build. Often select many models we want to build. Import the model. Instantiate the model. Fit the model. Make predictions. Once we made those predictions, we're normally going to make predictions for many different models. We store that data so that we can later plot it and look at other statistical metrics to decide what is the best model. Is the best model, like decisions you have, are model type, k-nearest neighbors versus decision tree, so actual completely different models themselves, or if I say k-nearest neighbors is the best model generally, within that model, what are the best hyperparameters? What's the best k-value? What's the best weight? What's the best scaling that I use for the different features? All things that we can tune, and we will tune in this class. That is the process of building out a supervised model. Yeah, what's up?
I thought it was interesting just to see the illustration of the underfitting using k of 100 by doing the predict proba, predict underscore proba, and all three, it's like 50%, 50%, 45%, 50% when you have k 100.
Yeah, so when we have k equals 100, if I looked at predict proba, well, I mean, it's going to change observation to observation, but you're going to see probably more similar. Instead of like, I really strongly believe it's one value or another, it's looking at so many data points that it's going to be kind of fuzzy on which data points are important, which ones aren't important. So I think that was just an instance of the specific row you were looking at, the specific value. But you will see that like more fuzziness and less certainty in the actual predictions. Okay, so before we take the break, last thing in this notebook, you're going to see lots of these for every single model we build, which will become useful eventually when you want to compare the different models. What are models useful for? So when are they the correct model? When are they the incorrect model to use? The simple answer for that question is always, it depends. You never know ahead of time which model to use. And a good story here is there's a company called, it's a grocery store chain, Harman Kardon? I'm saying it wrong. And there's this company that does, they employ like very, very serious statistical modelers, so PhDs in stats. And one of the things that they had asked their employees once, like the top employees, was we're going to give you 4 different domains: grocery analytics, insurance, like 2 other things as well. So very different types of data, and we want you to take a guess of which model, k-nearest neighbors, decision tree, like which type of model is going to perform the best. And the result was that, they were just, it was on average that they got, no better than just picking at chance. The reality is it doesn't matter if you have a PhD in statistics or not. Very rarely are you going to be able to say right off the bat, this type of model is going to be the best performing model. Because there's a lot of nuance to data that you won't necessarily understand. Thus, we don't just build one model. We build tens, hundreds of thousands of models, and we allow the statistics to inform us which one is better or worse. I have a friend who builds fraud models at Capital One, and he really does focus primarily on the actual modeling itself. He tells me in a given day he might be building 100 to 200 different models. Right? So you're building lots of models very quickly, because we just built out 100 models a second ago. Right? It doesn't take a lot of effort to build 100 models. So you build lots of them with lots of different types. So that's like the high level, but let's pretend we are focusing on this k-nearest neighbors model, and I want to decide, when does this work better or worse? The nice things about it is that it is a very eager learner, or actually I should call it it's a lazy learner. Does it say that here somewhere? Yeah, so that's basically saying model training is fast, which means it puts off all the like really deep calculations all the way to the end. So you can build this model very, very quickly, right? Because let's think about that. The training speed of a model should always be at the top of your mind. This is an important point. What happens when I build the model? Well, at that point it's saying, there's a data point here, there's a data point here, and there's a data point over here. Just remember where those data points are. So it's basically just building a dictionary of the locations. It's not doing anything more complicated to that. Of course, the con of this, I guess it doesn't really say it there, but it means it's going to be a lot slower to get your calculations, right? Because what does the calculation mean right now? I have a question mark. I need to calculate the distance here, and the distance there, and the distance there. There's a lot more work when I'm saying dot predict than there is when I'm saying dot fit. So normally models are going to be more expensive in the fitting or the prediction process. And if I'm doing that model that I'm going to swipe at the credit card reader that needs to run instantly, I probably want a model that's doing all the learning ahead of time as opposed to one that's doing a lot of calculations when I'm actually making the prediction. Nice things about it, in addition to it training quickly, is that classification and regression. I talked about how we can use it for either of those two types of models. It's easy to understand, it's easy to explain. Some models we're going to get into are black boxes where you don't exactly understand how it's working. You can't perfectly explain this feature is more important than another one. We sort of move in the direction every model gets a little bit deeper. But this one, super easy to understand and explain. I did it in, 5-10 minutes there. This just means that we can be a little bit more flexible in the types of models that we build. That'll make more sense in later classes, so I'll skip that one. What are disadvantages? It takes a lot more memory because we have to memorize all the data points. I only have 150 data points right now. What if I had 10 billion data points? Now I need to memorize the locations of all 10 million data points. Now that's pretty expensive there. Okay, so just say prediction phase can be much slower when we have a very large set of data points. The accuracy is normally not that great. This is not the most accurate model, probably is the least accurate model that we're going to look at, but it's very flexible. And this stuff I'll skip past for right now. But you can see there's some advantages to it. We can build it quickly, it's really flexible, use it in lots of circumstances. It's good as a baseline to compare your other models to. Downside is that there's many ways that it's expensive. It requires a lot of memory, requires a lot of compute when I actually want to get the predictions and so on. So that takes us to 808. Let's take, and I'll record this. So this was actually the project that I built, now a little over 4 years ago, or almost 4 years ago. And I think Hannah's project was a lot better than the one that I've created. I just want to give you other reference points. So I'll go through this quick, but just to give you other examples of something that's not necessarily work-related. I had moved to DC pretty recently before I started this class, or I was at least switching apartments around that time. So I wanted to, got excited about the web scraping stuff you guys covered last class, and I said, let me go to Craigslist, scrape all the listings for apartments and figure out what are the attributes that are more expensive that don't matter to me, what are the ones that are cheaper that do matter to me, just to optimize my apartment search. So what I'm normally looking for these projects is a problem statement, here's what I'm doing, an explanation of the data itself, examples of how you clean up the data, the models, and then some sort of finding. So it can be any type of project, and as long as you have a data set, right? As long as I pick any data set, you have columns of data, you can make a prediction for one of those columns of data. Hopefully it's something that actually is interesting, but any data really works. Yeah, so what was I doing? I just went through the problem statement. What sort of data was I looking at? Well, I looked at Craigslist, and on Craigslist we have a lot of different fields. And this was one of the reasons I did it too, because I wanted to get a variety of data. We have the listing name. We have the listing text, so like long text description. I have the price of the listing. I have images of the listing. I have a map that actually gives me latitude and longitude information about the listing. And then categorical features as well, such as are cats and dogs allowed? What's the number of bathrooms and bedrooms? So categorical features, the thing I'm predicting, price, the text descriptions, images, geospatial data. It's actually a lot on Craigslist. So I used Beautiful Soup, wrote some code to actually scrape the data, scraped a couple thousand listings over a period of a week or so. I just have some examples of code, and you don't need to have code in the final presentation. There's two deliverables. One is you're going to do a 5 to 10 minute presentation, start a class. And that's really just your normal PowerPoint presentation. I actually do limit you to do PowerPoint just because I need to get through these quickly. Normally they actually have 2 classes aligned to the final projects, and I hate wasting your time that way, so I pack it all into one class just so we have a bit more class time. But it does mean I need to standardize the format, so everyone's going to send me a PowerPoint, 4 or 5 slides, and send that to me ahead of time class. But if you want to, here's an example. I did some web scraping. This is what the code for the latitude and longitude looked like, and I was able to pull out the attributes for those actual values. I actually then used an API. I took the latitude and longitude values and I passed it into a Google Places API, which is free for up to 1,000 or 2,000 requests a day. Pass in latitude, longitude, and it passes back a bunch of locations of interest. And I was asking the question of, is there a gym nearby this place? Is there a grocery store? Is there a Starbucks? Just general things of what are the nearby places to this listing? Like grocery store matters to me because I don't have a car. So this is what the Google Places code looked like. Pass in latitude, longitude, ask for some attributes, get those back. And that's the only code I have in the whole presentation. The second deliverable, though, is normally code file. So Jupyter Notebook, Spider file, I don't care how you format it, but I do want to see the actual code. So you're going to be sending that to me as a GitHub deliverable. Okay, so I had a bunch of data. What did I do to clean it up? Well, I'm not going to go through all of these, but what are some examples? On Craigslist, people will often make their listing $0 or $1 million so that when you sort it, it either goes to the top or the bottom. Obviously, those aren't the real prices, so I had outliers. I had to figure out a way to clean those up. I had a lot of categorical values. Instead of saying cat exists, you're allowed to have a cat or not allowed to have a cat, Craigslist says woof woof or meow meow, so I had to change that to numbers so I can actually pass it into the model. So lots of things along those lines. There was a bunch of missing data. I had to build a separate model to actually impute some missing values, features that I found to be useful. So other things like that. A little bit of data visualization. One of the hypotheses I had was that listings that have more images are going to be more expensive because it's more likely to be from a real listing company. And I don't care about if it's coming from a listing company or not. I just wanted at that time the cheapest possible listing. So I scraped the number of images, just a count. And that's actually this chart, which shows you, in fact, that if you have more listings on Craigslist, you have somewhat of a linear relationship of an increase in price. So I actually optimized my search when I found this for listings that had a few, but less number of images. So I looked at other things like the housing type and the week of day that the posting came out, thinking that formal companies, maybe they do all their postings on Monday morning when they get into work, but then your average person who might have a cheaper listing is doing it on the weekend. Again, this is hypothesis driven. So I had an idea, I looked at a specific feature, I cleaned up that feature to answer that question, and then use that to gauge if I actually want to use it or not, as opposed to clean up everything all at the start. Okay, so then at the end, I built out a bunch of models. The models that I built out were random forest, ridge regression, lasso regression, and a linear regression. Those are the 4 I selected. We're going to learn all those models in this class. I found that random forest was the most predictive. The selected features that I used were these features. Maybe talk for a minute about why I selected these. And one of the things we'll learn in this class is how to determine for certain models the importance of a given feature. So what I was able to do, in this case, I didn't care so much of was my model accurate or inaccurate. I cared more of what are the attributes that are most aligned to increases in price. And we saw that those were the square footage, how big the listing is. Okay, so that's a given. Posting time, image number. What I found interesting, though, was that, where's my mouse? There we go. The number of gyms, grocery stores, and gyms and grocery stores nearby actually had quite an influential impact on the price of the listing. And the downside of this presentation, and what I normally see with projects, is either you spend a lot of time collecting the data, and for me, that was the case. Web scraping, APIs, I spent 90% of my project just doing that. And you're either going to spend a lot of time there or you're going to spend a lot of time modeling. Almost never have I seen people really get through both activities. So if you really want to get good with Python and web scraping and APIs and data transformations, then do a messy project like this one. If you want to get really good at the modeling, pick a nice clean Kaggle data set or something like that. You should pick it based off of the guidance you want from me. because I'm going to focus on what you're actually coding. Anyhow, the downside was I spent so much time web scraping that by the time I finished that, I had already got a place because I only had a couple weeks to actually make a choice. But the reality is that maybe not so much for selecting an apartment, but if I was using this information as someone who's listing an apartment, almost never do you actually see them include that there's a gym across the street or there's a grocery store across the street, but they're including it in the price. Like it's a latent factor, which is quite important for the actual price of the listing. So if I was a rental company, I would make sure to put that information like front and center. Hey, we are across the street from a grocery store. And so just some example of a finding from the project. That's what I'm looking for. Problem statement. Here's the data that you used. Here's how you cleaned up the data. Here's a couple models you built, and then some sort of finding, or what are your next steps, if you will, for the project. So hopefully, again, this gives you at least another example of what a project could look like. I've seen people who have they have video games online, and they want to actually determine which character set should I use that is going to be most predictive if I'll win or if I'll use. I've had people who have built out models. Many people have built out the sports predictions type of models. Those are perfectly fine. I've had one person who worked at an insurance company that had a team of individuals that were looking at claims, so the real data, looking at claims that were coming in, and they would just randomly, like the order that the claim came in, that's the order that they actually would respond to the claim. But certainly you can imagine, like let's pretend it's car insurance, that car exploding is a little bit more severe than I have my bumper scratched. So he built a model looking at some of the features, primarily the text of the claims coming in, and he would just run this every single morning, and he is using it just to prioritize which claims should he answer first, which ones can he wait till later on in the day. So that's another example of a model. Those are all model examples, and 90% of the projects I see fall into that category. You don't have to do that, though. So two other examples of projects I've seen that weren't pure models, but were useful for in the realm of data science. One was from 3 classes ago now. Someone who was working at the Treasury Department, and basically he's dealing with lots of different addresses. And he just built this whole set of routines for fuzzy matching, because he gets back handcrafted addresses. Someone's actually writing it in, and it's typed. There's typed addresses, but you get 111 North Street, and 111 N Street, and 111 NST dot. So there's a million different ways that you get the same address written, and he wanted to do something called entity detection or entity resolution to actually be able to summarize, well, here's the claims coming from this region of the world, or this specific block within New York, as an example. Another and final one I'll talk about now is I had one student from like 6 classes ago who worked at this nonprofit, and the process that she went through is she got in a bunch of global spending data on nonprofits globally, and she would get this from 20 different stakeholders within her company, all as CSV files. They all had pretty similar structure, but there was difference in column names, and columns were moved to different places, so a little bit of work she had to do there. So she would open up the 20 files, she would copy the data out into one single file, so a lot of copy and paste work. She would then take that file and she'd load it into a database, and this database was actually hosting the information that was shown on their website. So it was purely an automation project, but what did she do? She used pandas to read in all the files, used some Python to actually clean up the files to create this one single file of all the data combined, and then use something called SQL Alchemy, which we'll see later on in a class for database work to automate the process to load the data to the database. And her outcome of that was that she saved herself essentially 3-4 hours every single week. And again, it's something where I think she's actually left that company, but for a year or so when she was still there, it saved her a lot of work. And if this is something that saves you work and it at least improves your Python data set, even if it's not pure modeling, I'm okay with it. I'd prefer a modeling project. I think I have more guidance to give in that space. But again, a couple other ideas in terms of what these projects could look like. What I would like by next class, if possible, and next Tuesday at the very latest, is for you to Slack both Hannah and I 1 or 2 sentences. Here's the data set that I'm planning on using, which could be linked to Kaggle site, or I'm going to use this data from work. and here's what I want to do with it. I have this data set, and I want to predict X, Y, Z. Really, keep it simple. 1, 2 sentences, no more than a paragraph. I just want you to at least start thinking about this so that it doesn't get to the end of class and you're a week away from the final project, and that's when you actually start building out your project. Last note, if you're going to do something as using internal data, remember, you have to do a final presentation at the end. So make sure you're thinking of a data set that, even if you can't share the data, you can at least share the findings of the data or do somewhat of a presentation on it. And make sure it's not a sort of data set where it's going to take you 5 or 6 weeks before you actually get access to it. And that's, unfortunately, that's normally the case when you're doing work projects. Okay, cool. So that's overview of the project. I'll keep talking about it throughout the class. Let's get to our in-class exercise today. If you go back to Jupyter Notebook, the other one is the MBA KNN exercise. So go ahead and open that one up. And you're going to have the rest of class. I'll walk around, answer any questions. What you are doing is making a prediction for MBA player positions. I'm reading in the data set right here. Quick question. Does yours say to _ data set, or does it just say data set? Just, okay, good. So that's what it should say. Okay, so we have a bunch of features in this data set. I'm going to first dictate a couple that I want you to look at. First, the label. What is our response? What do I want you to make a prediction for? And by the way, as you might be able to tell by my height, I know nothing about basketball, so if you don't know anything about the data set, don't worry, I don't either. We have our guards, our forwards, and our centers. Those are 3 positions that we have in the data set. We're using the statistics about the player to make a classification prediction of what is the actual position of that player. Data to make a prediction of the position of the player. What I'm giving you are 5 features to start off with, though if you finish this, you certainly can go back and try out some features of your own. We have assists, steals, blocks, turnovers, personal fouls. So 5 attributes about the player. We're going to use those and say, can I use these features to make a prediction of the position of the player? So I've given you that setup. What are you going to do? You're going to build out a bunch of models. These are going to be KNN models for today because that's what we learned. So you need to first train a KNN model with k = 5. That's the first model. Just build it. Then you're going to get predictions for all the players, and you're going to store those predictions, giving me both the predictions and the predicted probabilities. Then repeat this process a couple times, doing it with k = 50. Calculate the predicted probabilities again. And really, that's like the core of the project. I expect most people to get through that so that you're going to have an opportunity then to really explore the data set. Go ahead, and I've given you a couple examples here of visualizations. I'm not going to go through them right now. But at the end here, a lot of open space. I want you to go through this process, try out different values themselves, so different features. I want you to try out different hyperparameters of the model, larger values of k. And since I'm only playing around with that one hyperparameter, the k value, see if you can actually play around with the other ones as well. See how they work. Look at the documentation. I'm purposely only showing you one. I want you to actually go through that activity of read documentation to understand how this works. And yeah, that's what we have. If you want to, you can copy and paste the code that I had from the accuracy perspective at the end of the notebook to see which models are doing better or worse. That's not really the mindset that I have right now. It's more so just get comfortable building the models themselves. Because again, we need to fix something next class before I trust those results. But again, if you want to play around with that just to have some sort of baseline as you're changing the models and the hyperparameters and the features you use, yes, please feel free to do that. So that is the rest of today's class. I'll walk around, answer any questions, and from time to time I'll come to the board and type some code here or there to give you some solutions. Any questions about the